Great. Cool. How's everyone doing? Excited for Halloween? Okay. I just asked this, but I think any interesting costumes? Any interesting costumes? Yes.
Well, I just wanted to say that Dr. Gilbert in the Trevor department always just
A cheetah?
a cheetah. Yeah, I think I'm just a nurse. It's like cheetah print, like a onesie, and then gross whiskers on it.
Is there a story behind this, or?
He's done it every year. I don't know.
Wow, really cool. I did not know that. I'll add that to my department trivia list.
Did we get extra credit for the best costumes?
No, but you'll win life points. Yeah. Cool. Okay, so let's go ahead and get started. I just have a couple quick announcements before we get started. So homework 5 is posted. This is a shorter assignment. This is on culvert and detention basin design. It's a shorter assignment, kind of along the same lines as homework 4, but I give you a little bit longer because we're still covering the material. So that'll be due November 7th, which is the Monday after this coming Monday. And then homework 6, again, is due November 15th. So a few weeks from today. Who here has decided on your group roles in terms of the preliminary design? I just want to get a sense. Has anyone figured out what your preliminary design is going to be? No? Okay, so I'd recommend figuring that out this week or next week, and just continuing to work on that up until November 15th. We'll get time to work on it in class starting next week, and then continuing up until the deadline. And I can postpone this if needed. It's just that we have fall break right after this. So it'll really be your last chance before we get into kind of the presentation week before where I can answer questions and things like that. So I'd like to get it done kind of early if you can. Okay. Any questions on the design project? Just general questions. And feel free to come see me in office hours Thursday, Tuesday, if you have any questions about the design project and what you should be doing. Any questions? Yes.
Calendar question. We have a week after Thanksgiving fall break in class.
There will be a in-week, a week in class, but we're going to be doing presentations for at least part of that.
Okay.
So you'll need to have your design pretty close to finished. Yeah. And we will, yeah, as I mentioned, we will be having reviewers from outside as well. So yeah, it will be good to continue working on that starting this week. Okay. Any questions? It sounds like there might be a couple questions. Any questions? Cool. You will be getting a good amount of time in class to work on this. Yeah. All right. Any last? Oh yes, Austin.
For areas, ours is kind of large area. You need to like see the entirety of the site.
So the important part is to identify the specific low water crossing where the issues are occurring. So just that portion of the site is really the key part. Yeah. Was there another question here? No? Cool. Any other questions about the design project? Okay, and I will be doing some in-class exercises, particularly in regard to the land cover and detention basin parts, just to give you a bit more guidance on those, because they are a little bit more difficult than the culvert and channel modifications. Okay. Any other questions on the design project? Okay, great. Well, let's go ahead and get started. So today we're going to be finishing up our discussion of culverts. Last time we introduced culverts. What are they? What are they for? Where do you put them? And what are the different types of culverts? We talked about the basic design problem for culverts, which is given a design discharge, your goal is to design the culvert dimensions to meet a desired headwater condition. You may also have to consider things like the inlet type, the material of the culvert, but primarily we're interested in designing the dimensions of the culvert, specifically the vertical dimension, which is what the equations that I gave you are designed to do. And we talked about different types of culvert control. So as a quick recap, what are the two types of culvert control when we're talking about culvert design? Yes? Right. So we have inlet control and we have outlet control. And does anyone want to volunteer and answer for what these types of control mean? What does inlet control mean, first of all? Yes.
Making sure that like all the water you get in. Maybe combining with and it's like having critical flow faster than anything.
So yeah, our overall design goal is to try to make sure that the culvert can accommodate the flow and achieve that desired headwater discharge. Inlet control and outlet control refer to the flow conditions within the culvert and thus what design procedure we need to use. So, and you mentioned it, but what is the condition for inlet control? Right. So exactly under inlet control, critical depth is achieved near the entrance. And what's the consequence of that? What's the consequence of that fact? Yes, so you'll have supercritical flow through most of the culvert. And in terms of our design process, what does it mean? Or what do we not have to worry about? Right, so for inlet control, the hydraulics throughout the rest of the culvert don't really matter for the design equation. What matters is just figuring out what's going on in that critical section. We don't need to perform a full backwater analysis to figure out what the headwater elevation is going to be. All we have to worry about is that critical section. And what about for outlet control? What is that? What does outlet control mean? Does anyone remember what outlet control means? Guesses? Yes?
Either pressurized or it's subcritical throughout the whole.
Exactly. So it's either pressurized flow or subcritical throughout the culvert length. And as we'll see today, and under outlet control conditions, the hydraulic conditions within the culvert matter for the design process. They matter in terms of how we're going to be computing the headwater depth. Okay, so outlet control is generally the more complex of the two. So very good. And at the end of class last time, I gave you the design equations for inlet control. There were two cases for inlet control design. The first is if you have an unsubmerged inlet, you use one set of equations, which we derived in class. And if you have a submerged inlet, you use a different set of equations. Okay, and both of these are partially empirical. So we have these empirical parameters K, M, and Z that we need to look up. One thing I wanted to show you, because I got a question about this after class, a lot of the procedures that I'm showing you today come from this manual for the hydraulic design of culverts. So I posted this under Canvas under Pages, but this is essentially probably the most comprehensive reference for culvert design. And we're going to be using it in class today to look up some of those empirical parameters. This gives you pretty much everything you would ever want to need to know about culverts. It's a 320-page long design manual that goes through all of the possible cases for culverts. So, obviously we're not going to be able to cover all of this in class. I just want to give you a quick introduction to the idea of culvert design and what you need to do. Okay, so that reference is there if you need it. So this is the Federal Highway Administration's design manual for culverts. There are also local design manuals for culverts that may have slightly different design procedures. Texas has its own culvert design procedures, and we'll talk a little bit later in class about what the differences between those two procedures might be. But I wanted you to be aware of that resource. So that's where you would ultimately get these parameters like K, M, Z, C, and Y. You look it up in a table for different culvert types. Okay. Great. Are there any questions on what we covered last time before I move on? Any questions about inlet control of culverts? Okay, so what I want to do now is give a chance to apply this procedure to a real world design problem. So we're going to be looking at an example of culvert design under inlet control. So this is inlet control. Okay, and what I want you to do is I want you to consider a circular culvert. Consider a circular culvert with a square edge and head wall. Okay, and the following conditions. Okay, so we have a proposed diameter of the culvert of 8 feet. We have a Manning's roughness in the culvert of 0.014. We have a design discharge of 400 cubic feet per second. And we have a bottom slope in the culvert of 1% or 0.01. And our desired headwater condition is we want the headwater depth to be less than 10 feet. And what we're going to do is we're going to evaluate whether this culvert is going to be sufficient to achieve that desired headwater depth. For instance, we may want the headwater to be less than 10 feet because over 10 feet, it'll be flooding the roadway that the culvert is underneath. So in this case, we just want the headwater depth to be less than 10 feet. And we need to check to make sure our culvert design meets that requirement. Okay, so the first thing we need to do is, well, we need to figure out which equations we're going to use, right? So first of all, is this submerged or unsubmerged? We don't know yet. So the first thing we have to do is we have to figure out if this culvert is submerged or unsubmerged. How can we do that? There's remember, if we go back to these equations, we have that the culvert is unsubmerged if this quantity here is less than 3.5, and it's submerged if this quantity here is greater than or equal to 4. By the way, what happens if it's between 3.5 and 4? What do we? Yeah, we interpolate between these two equations. Very good. Okay, so the first thing we have to do is figure out whether this is submerged or unsubmerged. So we're going to use this expression here. So I'll say first, determine if submerged or not. Okay, and our expression was KU times Q divided by A times D to the 1/2 power. If we substitute in our values, we're using US units, so KU is 1. Q is 400 cubic feet per second. Our area, well, what is our area here? So this would be pi r squared or pi d squared over 4. So this will be pi over 4 times 8 feet squared for the area. And then we have square root of the diameter. So this will be square root of 8 feet. And if you go ahead and evaluate this, what you will end up with is about 2.81. So is this submerged or is this unsubmerged? This is unsubmerged. Okay, so now we know what equation we need to use. Unsubmerged. All right, great. So we can now write out the equation that we need. We'll be using the unsubmerged equation. So I'll give you a second to just write that down. So we know that it's going to be unsubmerged. So we'll be using an equation that looks like this. We have HW over D is equal to capital HC over D. By the way, what is capital HC? Does anyone remember? It's the specific energy at the critical depth. So it'd be the critical depth plus U squared over 2G, right? Very good. Okay, so we have HC over D plus, and then we have this empirical portion K, which is a coefficient we're going to need to look up, times quantity KU Q over AD to the 1/2. So we've actually already evaluated this term. This should be 2.81. All to the M power plus Z. Okay, so we have a couple things we need to figure out. The first is we need to figure out what this K and M are. So how can we do that? Sorry? Yeah, let's go look it up in the manual. So we have a, what is this? A circular culvert with a square edge and head wall. All right, let's go look it up. And I happen to know what page it's on. It's on page 197. And let's just, let's say it's concrete. So we can just go to this first row here. And we see that for unsubmerged, we have K is equal to 0.0098 and M is equal to 2. So let's go and write those in. K is equal to 0.0098 and M is equal to 2.0. All right. And I didn't tell you what kind of, well, actually I did tell you what kind of inlet it is. But our Z, if you remember, this is going to be negative 0.5 times the bottom slope, which will end up being negative 0.5 times 0.01, which will equal 0.005. Okay, so we have these two terms. We figured these two out. We just need to figure out this term here, HC. Okay, so how can we do that? Well, we know that HC is equal to the critical depth plus the velocity head at critical flow. So let's try to figure out which each of these are going to be. So we need HC. All right. Okay, how can we figure out what the critical depth is going to be? Basically, what's the condition for a critical flow? What's the condition that has to hold if we have critical flow? Yes.
Minimum specific energy.
Minimum specific energy. I think I heard someone else say in terms of the numerical solution, crude number equal to 1, right? So let's start with that. So at critical depth, we have that the Froude number is equal to 1. Okay, Froude number is equal to the velocity times the square root of the top width over the square root of GA, if you remember from the notes. And we can square both sides, so we get U squared T over GA. And then we can re-express U also as Q over A. So we end up with Q squared T over GA cubed. And let's go ahead and just rearrange both sides. So for the critical condition, we have Q squared times T is equal to G times A cubed. Okay, and we know Q. We need to find the depth such that this equation works out. So let's do that. What we can do is we can look at our table for the hydraulic geometries. Okay, and we have for a circular channel section, we have that the area is given by this expression here, 1/8 times theta minus sine theta times the diameter squared. So theta here is this angle subtended by this triangle that originates from the radius, from the centroid of the circle. And we have the top width here. I'm going to use this first expression, sine 1/2 theta times d naught. So let's go write those down. We have that T is equal to sine of theta over 2 times d, or d is our diameter. And A is equal to 1/8 times theta minus sine theta times d squared. And if we plug those in, we end up with this kind of complicated expression. So I'm just going to say plug in. We end up with Q squared times sine theta over 2. I'm going to call this theta theta c to indicate that it's the angle at the critical depth. Sine theta c over 2 times d is equal to g times quantity 1/8 theta c minus sine theta c times d squared all cubed. All right. So let's group all of the theta terms on the left-hand side. If we just group all of the theta terms on the left-hand side, what we end up with is theta c minus sine theta c all cubed over sine theta c over 2 is equal to 8 cubed times q squared divided by g times d to the 5th power. If you take d squared to the 3rd and then divide by d, you get d to the 5th power. Okay, so this, we can't solve this explicitly. We have to solve numerically. And this is what you'll be doing on the homework. But if you do solve it, what you end up with is theta c, our angle at the critical depth, is equal to 3.691 radians. So I'll give you a second to write that down. This will be useful for homework 5. It's a very similar problem. Okay. And once you do that, we can find a relationship between the depth and the angle. So for a circular cross section, we have the following relationship. The depth is equal to d divided by 2 times 1 minus cosine of the angle theta c divided by 2. And if you evaluate this, what you get is HC is equal to 5.085 feet. Okay, so we know one component of that specific energy at the critical depth. Okay, so I'll give you a second to write that down. All right, now how can we figure out what the specific energy is? We have that HC, capital H of C, is equal to our critical depth plus UC squared over 2G. We have this term here. How can we figure out what this term is here? Very good. So we take it and we put it in terms of Q. We have HC plus Q squared over 2G times AC. I'm going to call it AC because it's the area at the critical depth. Okay. So very good. And how can we find AC now? Well, we could go back into that table and figure it out using the expression for the hydraulic geometry, the area. There's a slightly easier way. So for the critical depth condition, we have that this expression holds here. We can also just write this out, Q squared. We can basically divide by T so that we get Q squared is equal to G times A cubed over TC. Okay, and then if we substitute this in here, what we end up with is that this expression here, capital H of C is equal to little h of C plus, if we substitute in, what we end up with is AC over 2TC. Okay. And if we evaluate this, we end up with capital H of C is equal to 7.272 feet. Did I make a mistake there? Oh, yeah, there should be a squared in the denominator. Very good, thank you. Yeah, because we took u squared, which is equal to q squared over a squared. Very good, thank you for checking. All right, and with that, we have everything we need to solve this problem. Let's go back to our equation. We now have that HC is equal to, this entire term will be equal to 7.27 divided by 8. Let's go ahead and just evaluate this entire thing. I'll go write it out again. We have that HW divided by D is equal to 7.27 divided by 8, our diameter, plus, oh gosh, let me go back here, 0.0098 times 2.81 times 2, see if I can remember that, 0.0098. 2.81 squared minus 0.005. We evaluate this entire expression. What we should end up with is 0.982. So what is our headwater? What is our headwater depth? Well, we can find it just by multiplying this by the diameter. So the headwater is equal to 0.982 times 8 feet. What we'll end up with is 7.86 feet. Okay, so does our culvert meet the design criteria or no? Do we meet the design conditions? Yes. Why do we meet the design conditions? It's less than 10 feet. Very good. Cool. And with that, you have the design procedure for inlet control culverts. So that's basically all there is to it. Right? Are there any questions? Any questions on the inlet control design procedure before I move on? No? Okay, cool. Well, with that, because I don't have too much time today, what I'm going to do is I'm going to move on to outlet control culverts. So today, we're going to be looking at outlet control. This is the more difficult of the two in general. Okay, and we're going to be looking at two different conditions. We're going to be looking at full culvert flow. So this is the condition where it's pressurized. And we're going to be very briefly touching on partially full culvert flow. Okay. Full culvert flow, I can give you a closed form design procedure for solving it. But for partially full culvert flow, you're going to need to use a numerical method called the direct step method. This is basically something you need to code. So I'm not actually going to evaluate you on the direct step method. This is essentially very close to what HECRES is doing when it's computing the water surface profiles. So I'll very briefly touch on it at the end of class, but we're mostly going to be focusing on the full culvert flow, which is the form for which I can give you a closed form solution procedure. Okay. Great. So let's go ahead and talk about outlet control. So again, as you mentioned earlier in class, outlet control is when the culvert is either fully pressurized or it is subcritical throughout most of its length. This design condition here, the full culvert flow, refers to the case where it's pressurized. Partially full culvert flow refers to the case where it's subcritical throughout most of its length. So what I'm going to do is I'm going to first just give you the full culvert flow design equations. So we'll call this outlet control with a submerged culvert. Okay. So the essential idea here is to find the sum of the head losses across the culvert. So we'll be given a tailwater condition at the downstream end, and we'll want to find the sum of the head losses through the culvert such that we can reconstruct what the upstream headwater depth would be, given those head losses. That's essentially the design procedure. So what equation do you think we're going to use for the outlet control of the submerged inlet design? Energy equation, right? Very good. So it's again, we're considering only steady state. We're given a tailwater condition, and we're computing the sum of the head losses through the culvert. Okay, so basic idea. Use the energy equation. And find the sum of head losses through the culvert to find the headwater depth. And note here, we'll generally be given a tailwater condition. Okay, so what do you think the sources of head loss are for this problem? What are the sources of head loss? Any ideas? What are the major sources of head loss through the culvert? Friction, very good. So there are friction losses. Okay, what else? What other kind of losses are there? Yes. Exactly. So those are the other two losses. Yeah. So those are the three losses we'll be accounting for. So friction losses, entrance losses, and exit losses. All right. Very good. So let's go ahead and write that out. So for full culvert flow, the total head loss is as follows. We'll call the total head loss H, and it'll be equal to the sum of three different components. HE, the entrance losses, plus HF, the frictional losses, plus HO, the outlet or exit losses. So let me just label these. This is the total head loss. This is the entrance loss. This is the friction loss. And HO is the exit loss. Okay. And in general, we're going to assume that all three losses are functions of the velocity head. I.e. it'll look something like some constant K times U squared over 2G. Okay, so we're going to assume that all of these losses are some function of the velocity head at that point in the culvert. Great. Are there any questions before I start getting into the outlet control design equations? Any questions? Okay, cool. So let's go through each of these. I'm going to talk about the entrance loss, then the friction loss, and the exit loss, and then we're going to show how we can apply this to a outlet control culvert design problem. Okay. First, let's take a look at the entrance losses. So for the entrance loss, we have that our entrance loss is equal to KE, this is our entrance loss coefficient, times UE squared over 2G. So UE is our velocity at the entrance of the culvert. We can also write this as KE is equal to Q squared over 2G AE squared, where AE is the area at the entrance of the culvert. So let me label these. KE is a constant. UE is the velocity at entrance. And AE is the cross-sectional area at the entrance. And note that KE will generally be in the range of about 0.4 to 0.7. So that's just kind of a general range of what it should be. Are there any questions on any questions? No? No? Okay. Great. So our entrance losses will be of this form. With that, we can move to the frictional losses. I'll just give you a second to write this down. And let me just label this. This is the entrance loss. The frictional losses will also be of that form, but I'm going to write it a little bit differently. So the friction losses, we can express this as L times another number. What is that other variable? If L is the length of the culvert, the friction losses will be L times what? We talked a little bit about it earlier in class. Yes? Oh, sorry? So that's a good guess. So we talked a little bit about this in the first module of class. If the total frictional loss is equal to HF, then it'll be equal to some slope times the length of the culvert, right? So what would that slope be called? Yes.
Is it the EGL, the energy grid line?
Yeah, the slope of the energy grade line, which is called the friction slope, right? So we're going to think about it like that. So it'll be equal to the friction slope times the length of the culvert. So we talked a bit about the friction slope when we discussed Manning's equation. Under Manning's equation, the friction slope is assumed to be equal to the channel bottom slope, but in general, the friction slope is the slope of the energy grade line, right? So we can figure out what that friction slope is by using Manning's equation. This goes back to our derivation towards the beginning of class, but we have that Q, the discharge through our culvert, is equal to phi over N times A times R to the 2/3 power times the friction slope to the 1/2 power. Right. So this is Manning's equation, except instead of the bottom slope, we're using the friction slope for this term here. So note that Manning's equation is a special case where the bottom slope and the friction slope are equal. But we can figure out what the friction slope is by using this equation here. Yes?
When we were talking about length earlier, the right triangle and not an bottom.
Right. So we're assuming that that basically they're very close. So it's an approximation for the hypotenuse.
Okay.
Yeah. So technically, yeah, you're right. But we can use this approximation and we can figure out the friction slope by basically isolating the friction slope from this equation on the left-hand side. Okay, so we have that SF is equal to, if we rearrange this, we get Q squared times N squared divided by phi squared times A squared times R to the 4/3 power. And thus the frictional losses will be equal to SF times L, which will just be the same expression, Q squared, N squared over phi squared, A squared, R to the 4/3, all times the length of the culvert L. And note that if you rearrange these terms, it'll end up being of the form some constant KF times U squared over 2G. Did I forget a 2G? No, I didn't. Okay. Yeah, if you rearrange this, you can put it in terms of a KF times the velocity head, because we have this Q squared over A squared term in there. So basically, if KF has 2G on the numerator, you can put it in this form as well. Okay. But this here is the expression that we use for the friction loss. All right, and with that, all we have left is the exit loss. Are there any questions on the friction losses? So this is using kind of some of the material we talked about at the beginning of class with the Chasey-Manning approximation. So this comes from the Chasey-Manning equation.
Can you get the entrance loss from before?
Yeah, the entrance loss we wrote here. This constant you look up in a table based on the type of inlet you have. Yeah. Very good. All right, and all we have left to worry about is the exit losses. And the exit losses will be very similar to the entrance losses. Our exit losses will be of the form HO is equal to some constant KO that depends on the inlet type times the following quantity, UO squared over 2G. So UO is the velocity of the water at the outlet minus UD squared over 2G, where UD is the velocity downstream of the culvert. So let me just write that out. This is the velocity downstream of the culvert. And UO is the velocity at the culvert exit or at the outlet. So in other words, UD is kind of the velocity in the channel downstream of the culvert. Okay, so we can also write this in terms of Q and the area instead of the velocity, which we'll often have a better idea of. So we can write this as KO over 2G times 1 over AO squared minus 1 over AD squared times Q squared, where this is the outlet cross-sectional area. And this is the area of the downstream channel. Okay. So for the exit losses, we're accounting for both the velocity at the outlet and at the channel downstream. Note that KO will be equal to 1 for abrupt transitions and 0.3 for gradual transitions. As for where these numbers come from, they come from those design manuals like the one I showed you at the beginning of class. It's based on empirical studies. All right. Cool, and with that, we have all three of our losses. Let's go ahead and sum them together. So we're going to sum losses together. And the total loss will be equal to H, which is equal to quantity. I'm going to put it in terms of Q squared over 2G. So we'll have quantity KE, the entrance loss coefficient, divided by AE squared, plus quantity 2G N squared times L divided by phi squared times the hydraulic radius to the 4/3 power times A squared. So this term represents the frictional losses. And then finally, we have plus KO times quantity 1 over AO squared, the outlet cross-sectional area, minus 1 over AD squared, the cross-sectional area downstream in the channel, all times Q squared over 2G. So note that I rearranged the friction term here so that we can kind of express it in the same way as the others. So I added a 2G in the numerator. All right. So what's one simplification we can make here if the culvert is completely full? Yes?
All the culvert areas are the same.
Exactly. So if the culvert is completely full, then all of these areas, the AE, and the AO, they all just become A. So we can do that, and if we do so, we can pull out the A and simplify. So I'm going to say H is equal to, let's just write Q squared over 2G A squared. So we factored out that cross-sectional area from everything. And what we get is KE, the entrance loss coefficient, plus 2G N squared L over phi squared times R, the hydraulic radius to the 4/3 power. Plus, and we can factor out the A from here by writing it as follows: KO times 1 minus A squared over AD squared. And that allows us to simplify it. And we can make one further simplification. And this is how it's usually specified in the drainage design manuals, although it kind of makes it a little bit less general. If we assume tailwater velocity is negligible and an abrupt transition, we can simplify this final term. This final term will essentially just go to 1. And we arrive at kind of the standard form of the outlet control equation for submerged culverts, which I will write. Just give you a second to finish writing this down. Everyone's got it. So we arrive at the final form of the equation. We have that the total head loss is equal to Q squared over 2G times A squared times quantity KE, the entrance loss coefficient, plus 2G times Manning's roughness squared times the length of the culvert divided by phi squared times the hydraulic radius to the 4/3 power plus 1. And this is our final expression for the total losses. That's right, total head losses. All right, and we're pretty much there. Oh, again, this comes from Manning's equation. So phi is equal to 1.49 for US units, just as a reminder, or 1 for SI units. Okay, so with that, what can we do now to figure out what the headwater depth is? So we have the total losses through the culvert. We have the tailwater depth. How can we solve for the headwater depth based on what we know? What equation would we use in this context? Yeah, sorry, just checking. Cool, so with that, we can apply the energy equation. Okay, so what do we have here? Okay, so we have our depth at the upstream end, so that'll be HW. We have our elevation, so our elevation difference between the top and the bottom. Actually, let me draw this out. I think it'll make it a bit easier to see here. Okay, so if we got our culvert. Oh gosh, okay, I need my line drawing tool. Let's draw this out. We have our culvert. We have our embankment. Let's just say it's submerged on both ends. Okay, so this here is our tailwater depth. Good luck. This here is our headwater depth. Okay, we may have some velocity upstream. I'll call this UU. We may have some velocity downstream. I'll call this UD. What other component do we need for the energy equation? What other term do we need here?
Elevation.
The elevation difference. So we may not know the absolute elevation, but we know generally the slope and we know the length. So this elevation difference we can express as L times S naught. And again, I'm kind of playing fast and loose with this this length term here, but this is approximately the elevation difference between the two sides. Okay, so let's go ahead and write out our energy equation. We have for our energy equation, what do we have on our left-hand side? So we have the depth, that is HW, right? We have the elevation difference, which is L times S naught, our slope, channel bottom slope. And then we have the velocity head term, which is UU squared over 2G. Okay, and then on the second point, at the downstream end, we have our tailwater depth plus our velocity head UD squared over 2G. Do we have anything else on this side? Right, good, cool. Just checking. Okay, so plus our losses. Very good. Okay, and often what will be the case is that in design manuals, they will assume that the upstream velocity is approximately equal to the downstream velocity. And if you do that, you can simplify this equation a bit and you will get HW, our headwater depth, which we're looking for, is equal to our head losses plus the tailwater plus the difference in the elevation head. Actually, sorry, there should be a minus here. And if we just want to be explicit here, we can write out the head losses. We'll get TW minus the length times the bottom slope plus our derived expression for the head losses, which is the entrance coefficient plus 2G times Manning's roughness times the length of the culvert divided by phi squared times R, our hydraulic radius to the 4/3 power, plus 1 times Q squared over 2G A squared. And that is our final expression for the outlet control design equation for submerged conditions. So there you go. Cool. Are there any questions on that on the outlet control design procedure? Cool. I'm going to give a quick example of applying this to a problem. Again, it'll be similar to something in your homework. Let's go ahead and apply this to an example. This will probably be the last thing we do today. Okay, so what I want to do is compute the headwater depth for a circular, for the same culvert as we looked at previously. Under outlet control conditions. So again, we have D is equal to 8 feet. That's our diameter. We have Manning's roughness equal to 0.014. Our entrance loss coefficient, we'll say, is equal to 0.5. Our length is equal to 50 feet. Our design discharge now we'll say is 600 cubic feet per second. Our bottom slope is, oh, it's actually going to be different now. So it'll be 0.004. And our tailwater is going to be given as 8.5 feet. So this is still the same shape of culvert with the square wing walls and head wall. But in this case, we're assuming outlet control conditions. And we're going to try to compute what the headwater depth is. Okay, so we know that just looking at this, we know that the tailwater is submerged, right? How can we figure out if the top side is submerged or not? How can we figure out if the upper end is submerged or not? Right, because the equation I gave you, it only applies if both ends are submerged, right? So how do we know if upstream end is submerged? Are there any ideas? Are there any ideas? So it turns out that checking for whether the upstream end is submerged or not depends on what design manual you use. So the Federal Highway Administration design manual, for instance, will say that if the bottom end is submerged, you can just assume the top end is also submerged. If you are working in Texas, though, Texas has a different procedure for determining if the upstream end is submerged or not. What we can do if we're following the Texas procedure is if we have a culvert, right? And we know that the bottom end is submerged. One way that we can check, let's say our culvert looks like this. And we have that the tailwater is at 8.5 feet. The diameter is at 8 feet. What's a conservative way that we could tell whether this upstream end is going to be submerged or not? So let's think about if we look at the hydraulic grade line. Let's say we have the, we're interested in the hydraulic grade line. And maybe there's some exit losses or something that'll make it go down here. Like typically, you would have a higher hydraulic grade line right before the exit. Let's just be conservative. We can estimate the hydraulic grade line through the culvert by looking at the friction slope. Okay. So if we plot the friction slope, we can compute the friction slope and plot it. And if the friction slope is steeper than the bottom slope, then that means that the upstream end will also be submerged, right? Because the hydraulic grade line will be above the top of the culvert. Okay, so the check we're going to do is if SF is steeper than S naught, if the friction slope is steeper than the channel bottom slope, we can assume conservatively that the inlet is submerged. Are there any questions about, does this make sense? Any questions? Yes?
This is only for HGL, not EGL, where there's velocity in.
Right. Yeah. So this we're estimating the HGL through the culvert by looking at the friction slope, because we know that the HGL in the culvert is going to decay as a function of that friction, right? So the HGL will give us kind of the slope of the water surface or the pressure surface through that culvert. And thus we can estimate what it's going to be conservatively at the upstream side. Note that, yeah, the head will also drop at the entrance and the exit, but we're estimating conservatively here to see if it's submerged or not. So this is the approach that's used in Texas. Like I said, though, this isn't universal. Other guidelines will use different procedures. Did you have a question? Oh, no? Okay. Great. So let's go ahead and do that. Let's look at the friction slope. Our expression for the friction slope is given by n squared times q squared divided by phi squared times the hydraulic radius to the 4/3 times a squared. So this is just coming from our expression from the friction slope from earlier. This comes from the Chasey-Manning equation. And if we plug in our values, we get 0.014 squared times 600 cubic feet per second squared divided by, we're in US units, so this will be 1.49 squared. Hydraulic radius, we computed this earlier, but it ended up being 2 to the 4/3 power. And our area will be about 50.3 squared. Actually, sorry, I don't think we computed the hydraulic radius earlier. In any case, R is equal to A over P, which is equal to pi times diameter squared over 4 times 1 over pi d. And that'll end up being 2 feet. And the area is just equal to pi d squared over 4, which will end up being about 50.3 feet squared. All right, and if we compute this, what we'll end up with is 0.005. Okay, so is the inlet going to be submerged or unsubmerged based on this criteria? It'll be submerged. So SF is greater than S naught, thus inlet is submerged. So what I'm going to let you do for the final 5 minutes is I want you to apply this equation here to determine the headwater depth. Okay, and I'll give you about 5 minutes to do that. I'll check on you, and then after that, we'll be done. Okay. Cool. We're about to run out of time. Does anyone have an answer they want to volunteer? Anyone have an answer they are confident in? Jack? Yes, that's correct. So it should be about 11.9. All right. Great. Have a happy Halloween. Be safe, everybody. And well, tell me about your costumes. We'll get back.